Hello, I'm Maxime, and today I'll be telling you about YJIT. So the program today, a little bit about YJIT, why we're building YJIT inside of CRuby, how it works, and then some performance results and the next steps that we plan to take to unlock even higher performance. So YJIT, why not JIT? The name stands for YJIT because it compiles your bytecode into machine code, or also yet another Ruby JIT because it's far from being the first attempt at building a just-in-time compiler for Ruby. So this project was built at Shopify and it's fully open source and was created with the hope of eventually upstreaming and merging it into CRuby. The objective is to produce speedups on real-world software. For us, real-world software means largely web workloads like Ruby on Rails because we do a lot of that at Shopify. CRuby is a very complex code base, so the approach that we've taken is kind of incremental, where we gradually build the JIT compiler, and for everything we don't support, we fall back to the Ruby interpreter. And then over time, we increase the amount of things that we support in the JIT and get more sophisticated. The benefits of our approach is that we're highly compatible with all existing Ruby code, and we're able to support all of the latest Ruby features. So this project is not just me, it's a project led by an awesome team in the Ruby and Rails infrastructure group at Shopify with multiple major contributions from GitHub. In the space of Ruby JITs, there's been many other projects. There's CRuby, there's MJIT, there's TruffleRuby, there's Mir, there's Maglev, and there's many others that are no longer maintained as well. I'll just talk quickly about MJIT and TruffleRuby. So MJIT is already integrated inside of CRuby. It's based on GCC. Some of its strengths are because it's built inside of CRuby, it's compatible with the latest Ruby features. It offers good speedups on smaller benchmarks, and it's visually supported on multiple platforms. In terms of trade-offs, it performs best on smaller synthetic benchmarks, but it doesn't always yield speedups on real-world software. We think this is in part because GCC is not really equipped to optimize dynamically typed code, and MJIT has limited control over the compilation pipeline. So it generates C code that's then fed into GCC, and GCC does whatever GCC does. TruffleRuby is an alternative implementation of Ruby based on the Truffle and Graal platform. It's in active development. It has a powerful optimizer based on partial evaluation. It can offer huge speedups over CRuby on many benchmarks, and it has pretty good support for C extensions. But in terms of trade-offs, the warm-up time, that is the time that your program takes to get up to speed, can be sometimes lengthy, up to several minutes. There's significantly increased memory usage. And because it's a reimplementation of Ruby, it's not 100% compatible. Language compatibility is not just a problem in the Ruby sphere. I would say every time that you have a language where there's an independent reimplementation, it's kind of typical to see that alternative implementations are lagging a little bit in terms of compatibility. JIT is an extremely impressive project that's well loved by the community, but it's trailing a little bit behind in terms of compatibility with the Lua language. PyPy is also a very impressive academic project that's clearly faster than CPython in many cases. But again, they're trailing a little bit behind Python in terms of compatibility. And that's why we chose to try to build YJIT inside of CRuby, because we thought that even though it might be more difficult to build a JIT inside of CRuby as opposed to do a re-implementation from scratch, like a clean room implementation, it has the benefit that we can be very compatible with existing Ruby code. Now a little bit about how YJIT optimizes Ruby. So Ruby is a language that's very difficult to optimize. There's an article dating all the way back from 2012 that goes into some of the many reasons why that's still relevant today. In terms of the things that we had to contend with, every operation on every basic type can be redefined. So you can redefine things like the addition operator. You can redefine the meaning of x equals not nil. You can redefine methods at any time. Constants are not actually constants. With the bindings object, sometimes you have callees that can read and write variables inside of callers. The logic for method calls in Ruby is very complex. Like if you look at Ruby under microscope, like there's 11 different kinds of method dispatch in CRuby. And real-world Ruby code tends to have a lot of small methods. So because there's a lot of small methods, there's like not a lot of meat for a just-in-time compiler to optimize in there. And then there's the C extensions API that I'm going to touch on later. In addition to this, inside of every primitive operator in Ruby, there's a lot of complexity. So this is the code for the plus, the addition operator inside of CRuby. And as you can see, like it's handling a lot of different cases. Like if you want to do a fixed num addition where you're adding integers, it has to check, are the two values that I'm adding integers? Did someone redefine the addition operator for integers? If all of this checks out, then I'm going to do an integer addition. Otherwise, I'm going to check if the values are floating point numbers. I'm going to check that floating point addition has not been redefined, and then do a floating point addition, and so on, right? This is also defined for strings and for adding arrays together. So if you want to generate machine code for Ruby, you want to strip away all this complexity. You want to strip away all of these dynamic checks. And yeah, so the question is like, how do you remove all of this hidden complexity behind the scenes? In YJIT, we use a technique called lazy basic block versioning. This is based on research work that I started in my PhD. It's a technique to do type specialization of programs without doing costly whole program type analysis. And it's also an alternative JIT compiler architecture that works at a lower level of granularity. So if compilers like mJIT are typically method-based, which means that they compile entire methods at a time. With lazy basic block versioning, we work at smaller level of granularity, that of basic blocks. So we compile only the bits of methods that actually get executed. And there's a small but diverse body of literature. The first paper we published about this was at eCube 2015, and it goes into like the basics of how the technique works. Then we published a second paper about interprocedural extensions to this. There's also been a paper about using this technique to optimize functional programming languages such as Scheme, and also on how to optimize gradual typing. So there's two key components to this technique. The first is the versioning of basic blocks, where we generate multiple versions of code that are specialized based on types in a given context. The second component is the lazy generation of code. So that's when we generate code only when needed, truly just in time. I would say this technique is maybe like the most just in time type of JIT that you could have, where it tries to capture type information as late as possible. And it's a little bit like lazy evaluation for code. So those are the types that we track inside of YJIT when we specialize code. We track things like whether a value could be false or true or nil, whether it can be a fixed num, a floating point number, a symbol, an object that has properties on it, arrays, hashes, and strings. So just to give you a little bit of an example to understand how the technique works, if we have a piece of code that checks if n is a fixed num, and if n is a fixed num, it executes block B, otherwise it executes block C, and then it merges it into block D. In terms of a control flow graph, this is going to look something like this. So if n is a fixed num, we take the true branch, we go to B. If n is not a fixed num, we take the false branch, we go to C. And then we merge inside of block D. So what we can see here is that if we take the true branch, then inside of block B, we know that n is a fixed num. So that's like a fact that we know for sure. And inside of block C, we know that n is not a fixed num. But because we're merging in D, we know that n is either a fixed num or not a fixed num. So we know nothing at all. So what can we do about this? Well, by generating multiple versions of code, we can do what's called tail duplication. And we end up with two versions of block D. D prime, where we know that n is a fixed num, and D prime prime, where we know that n is not a fixed num. So yeah, that's it. Compilation solved. Well, maybe not quite, because like this is a toy example, right? But real world control flow graphs for real methods can look something more like this. And you can imagine if you were going to do tail duplication and kind of like double the size of your control flow graph for every conditional branch, you would end up with a code size explosion. So what can we do about this? Well, the key innovation here is the laziness. So in an example like this, it's pretty typical in real world programs that variables don't have every possible type at runtime. So we might find in our program that n is always a fixed num and is never not a fixed num. So with LBBV, we only compile the case, if n is a fixed num, we only compile the true branch, and we don't generate code for a false branch. So we're actually gaining some information about types, and we're also generating less code. And what we find in practice is that most blocks end up having only one version, with a small percentage with 2 versions, and so on and so on. So there's no code size explosion. Another trick that we use in YJIT is what we call a runtime value promotion. So in a JIT, we often want to specialize codes based on types seen at runtime. Typically in traditional JIT compilers, this is done by having like first a profiling pass where we run the code in profiling mode, we gather type information, and then we recompile like a specialized version of the code and we use the optimization and so on and so on. We use a technique that's based on Psycho, which was a predecessor to PyPy, and we defer compilation as late as possible. So we basically hold off to generate code until we can observe the types that are seen at runtime. So the compiler can like peek at the values that are actually like flowing inside of the program. So this is based on a paper that was published all the way back in 2004 on Psycho for the JIT compiler for Python, which was a predecessor to the PyPy project. So just to look at a simple example, here we have a method get that takes 2 arguments, obj and idx, and that's going to perform an indexing operation. So if we disassemble this to look at the YARV bytecode that gets generated, we're going to get something like this. So we have 4 bytecode instructions. First, get local, that gets the obj variable and puts them on the stack. Then we're going to get the idx parameter, push them on the stack. Then we have op aref, which just does the indexing operation. And finally, leave, that's going to return the results. So in our little example here, we have 2 calls to get, one that takes an array and an integer index, and one that takes a hash and a symbol key. So when YJIT compiles this, what it's going to do is that it's going to generate code for the get locals, and then it's going to install what we call a stub that's going to delay compilation until we get to that point in the program. Then when we get to that point in the program, we're going to peek at the types that we see. And in this case, the first time we call this, we have an array and an integer key. We're going to generate guards and specialized code that check. For the case where we have an array and an integer key, we generate an optimized array get. And then we install a stub to handle other possible cases in the future. Then if we call our get method a second time with a hash argument, we're going to go and install additional machine codes that we're going to patch into this program to handle the optimized hash get and so on. So we're only generating as much code as we need to handle the types that we see in the program. So now for some performance results. This graph here shows the performance of MJIT and YJIT compared to the Ruby interpreter, where the Ruby interpreter is normalized to 1.0. So every bar that's above 1 is where we're faster than the interpreter, and under 1 would be slower than the interpreter. The benchmark at the left is opt-caret that we've included because it's kind of like a classic in the Ruby community. And all of the other benchmarks are benchmarks that are based on what we would call like real-world Ruby gems and real-world software. So for YJIT, we've been really focused on optimizing software like Railsbench. And what we can see is that on pretty much all of the real-world benchmarks, we do better than the interpreter. We always do better than the interpreter, and we also outperform YJIT by a pretty wide margin. So here on Railsbench, we're doing like a 24% speed up. We don't outperform MJIT on opt-caret because that's not really a workload that we've been optimizing for. So if you're using opt-caret in production, maybe don't run YJIT. But in general, what we can see is that if we feed the code generated by YJIT to a CPU, the CPU is happy. More recently, we've started having a small deployment of YJIT in production at Shopify, where we're serving a small percentage of the requests with YJIT. And what we observe is something like a 3 to 5% speed up at the moment. You might be asking, why aren't you seeing more of a speed up? There's a couple of reasons for that. The first is that storefront renderer is a pretty huge piece of software. It has something like 10,000 methods that get executed at runtime. The other piece of that puzzle, I would say, is that there's also things like caching. So a lot of times, like storefront renderer, when it wants to serve a request, it has to fetch some data in a cache that lives on our machine, and that takes 5 milliseconds. And there's nothing that we can do to speed that up in YJIT. But I think those problems might get resolved in the future. But I think even more important than performance, our biggest achievement is compatibility. So we're passing all of the CRuby tests. We're also able to match Ruby head in the Shopify core CI. We're matching Ruby head in the GitHub backend CI. And we're also matching Ruby head in the Shopify storefront runner CI. Like I said, we also have like a small deployment in production that's been pretty seamless so far. So from here, everything is sunshine and rainbows, right? Well, maybe not quite. So I think when we talk about just-in-time compilers, people imagine that it's like this really advanced, really powerful piece of technology. And if you take a JIT compiler and you install it in something like CRuby, you get a really fast, sophisticated machine. But what we've produced in reality is maybe a little bit more like this. So it's faster than it was before, but it's maybe not as fast as it could be. Why is that? Well, because race cars aren't just regular cars with more powerful engines. They also have more aerodynamic design. They can channel airflow to cool the engine. They have a lighter body. They have racing tires, racing suspension, high-performance brakes, and special tuning. So if you want to engineer a system to get maximum performance, you need to take a holistic approach where all of the pieces fit together really well, and you eliminate all of the bottlenecks. But engineering always involves trade-offs. And in the case of CRuby, the design priorities for an interpreter are different. So like CRuby has evolved over 20 years to optimize the performance of an interpreter. When you throw a just-in-time compiler into the picture, maybe the priorities are slightly different. So there's a little bit, like those things are pulling a little bit in different directions. I think that to be fast, to make CRuby faster, adding one or more JIT compilers or having like a multi-layer JIT is not enough. We need to do a little bit of redesign work, maybe. I'm not suggesting that we should rewrite all of CRuby. That's completely unrealistic. But maybe we can target areas where the JIT compiler needs to interface with CRuby, or look at the biggest performance bottlenecks, or ask ourselves what are some things that we could easily improve to reduce bottlenecks. And in the process, we can help both YJIT and MJIT. So we have a couple of ideas on how to improve CRuby performance. Some of these we're already looking at. Kevin Newton is working on finer-grained constant cache invalidation, which should yield some nice speedups. We're also looking at an object model based on object shapes. That's a technology that was pioneered all the way back in Smalltalk. Smalltalk is one of the predecessors to Ruby, we could say. And I think we could also have potentially like a faster calling convention. So what do you want to do if you try out YJIT? Well, I said earlier, this project was created with the hope of eventually upstreaming. After I gave a talk recently at RubyCagi, we've actually been invited to merge into CRuby. Now it's done, it's official. YJIT is going to be coming to So YJIT is going to be coming to 3.1.0 Preview 1 and hopefully be included in Ruby 3.1. So if you want to try YJIT, you can take one of multiple approaches. You can take the lazy approach and wait for YJIT to come to you in Ruby 3.1. If you're very eager, you could download and install Ruby 3.1.0 Preview 1. If you do, make sure that you pass the -- YJIT command line option, because YJIT is still considered an experimental feature and it's disabled by default. We've also added a command line. We've also added an environment variable, Ruby YJIT enable. Just if you have like a CI pipeline where it's not convenient to pass -- YJIT, the environment variable might work out better. You can also use Ruby builds to build CRuby from source, or you can also build a Ruby head from source. It's surprisingly not difficult to do. Yeah, and let's talk a little bit about expectations and limitations. So I've talked about performance results. Currently, YJIT only supports macOS and Linux on x86-64. Why only those platforms? Well, in part because like the Shopify servers and most of the servers in the world currently are running x86-64, but also because this project is still pretty young. We've been working on it for 1 year, and we thought, you know, if we want to prototype and we want to progress faster in the project, we're only going to support one platform to get started. That's going to change in the future. If you run YJIT, you're likely to see a speed up somewhere between 5 and 30%, maybe more if you're lucky. But one case where it doesn't perform as well is when running something like unit tests, for example. Typically, when you're running unit tests, you're running like a lot of code, you're testing a lot of different things. And all of that code that you're running is not running for very long, right? You might call a method 5 times, then you're done, you test something else. So it's possible for unit tests that you're actually going to see a performance decrease. There's a command line arguments that you can play with to try to get a speed up. Yeah, and I would say it's pretty well tested. Like I said, we have a small production deployment, but it's possible you could run into bugs. If you do run into bugs, it would be helpful to us if you report them, if you get in touch with us. Also, right now, we don't have a garbage collector for code. So if you have a program that generates a lot of code, that does eval over and over and over and over, it's possible that you could like run out of executable memory and then crash. That's going to get fixed in the future. But yeah, there's some specific use cases where you could run into that problem. JIT compilers typically use more memory. That's because like we need to generate machine code, but we also need like a certain amount of metadata about your program. With the default parameters for YJIT, you're likely to use about 300 megabytes more memory. That is configurable, and that's also something that we're going to improve. And lastly, we've been really focused on web workloads, so like we don't optimize things like floating point computation at all. So if you had something that was like numerically heavy, it's possible it wouldn't perform as well. But feel free to try it and let us know. If you want to use YJIT and you want to get the best performance possible, I've compiled like some performance advice. First thing to remember is that, like I said, YJIT is still pretty young, still a pretty basic compiler. It has no method inlining. When you call .each, it does the same thing as the interpreter, right? So it calls like a C function, which then calls back into your Ruby code. And method calls in CRuby are actually pretty costly, pretty slow. So if you want the best performance possible, don't use trace point because that's basically going to disable the JIT compiler. Try to write larger methods, like larger and flatter, that do less method calls, have less indirections. You might also get better performance with while or until loops rather than something like .each, because that avoids like calling into C code and back into Ruby. Yeah, so I realized that this performance advice is not necessarily practical, because what I'm basically asking you to do if you want to get the best performance possible is to kind of like pre-chew your code because the compiler is too basic. But I think you don't necessarily have to rewrite all of your code to have a big impact. What you might find in practice is that, you know, your code might behave like based on the Pareto principle, where 10% of your code does 90% of the work, or 5% of your code does 95% of the work. So you could use like a profiler like RBSpy to find out what are the functions that run the most in your software, and you can make some small adjustments to these functions, a little bit of trial and error, and actually like get a big performance difference. Yeah, and the other thing is like we can't optimize C extensions. So C extensions are a little bit like a black box where when you're calling into C code, and with the JIT compiler, we can't do anything about it. So I think this is a little bit of a catch-22 because the story in Ruby is a little bit the same as in the world of Python, right? Where people assume that Ruby is slow, so they get told if performance is a problem, just rewrite those performance-sensitive parts of the code in C. But when you do that, the JIT compiler can't optimize that code. So at the end of the day, it's like you rewrote part of the code in C, but that's going to get in the way of performance optimization with a JIT compiler. I think this might not be relevant today, but eventually, as we get better JIT compilers for Ruby, it's maybe going to make sense to not tell people anymore to rewrite code in C and to sort of repatriate some amount of that C code back into Ruby land and have more of like a pure Ruby implementation of software. Like I said, like I don't think we're quite there with YJIT, but eventually this might turn out to be the case. So looking forward. In terms of future plans, we want to bring various design improvements to CRuby, some of which I've touched on earlier. We want to implement a garbage collector for code to improve memory usage. I'd like to look at how YJIT can optimize ERB template rendering, because that's commonly used in Rails applications. We want to tackle inlining and more sophisticated optimizations. And we also want to make YJIT more portable, add ARM64 support, because it's becoming more relevant, especially with the new Mac M1s coming on the scene. In terms of collaboration with the Ruby core devs, I would say just-in-time compilers are more complex than interpreters, so that makes it harder to refactor them. So stability is good for us. Mats has stated that Ruby will be more stable from now on. There'll be more focus on performance and maybe less language changes. That's good for us. I think in terms of things that could hurt YJIT and maybe also MJIT, it would be like major changes to the Ruby internals, like the Ruby bytecode, adding more complexity in special cases, adding more different kinds of method calls, or more complex instance variable lookups. It might be a little bit difficult for YJIT to catch up if those things were to change. I think YJIT and MJIT have pretty similar needs. So our plan is to upstream things like object shapes and new constant cache separately from YJIT, so that both YJIT and MJIT can benefit from those improvements. I think we might also be able to design a faster calling convention. And yeah, we're also open to discussing like other various improvements to CRuby. In conclusion, still pretty early in the YJIT project. I think our results are pretty good, but still kind of modest. I think we have a path towards much bigger speedups in the future. We're building YJIT inside of CRuby because there's a huge compatibility advantage, and we're already passing all the CRuby tests. And this compiler is built on a technique called lazy basic block versioning, which is kind of like lazy evaluation for code that specializes code based on the types that you're seeing at runtime. If you're curious to learn more about the technique, I put references to 2 papers that explain a little bit more about basic block versioning. And if you'd like to reach out and talk about compilers, I put my Shopify email address here. Thank you. Sure, okay. MC Aaron will take your questions.
We have about 3 minutes for questions. I have some here from the Discord. Anyone here have questions? All right, I will start with a question from the Discord, and then you can think about them. Let's see. Kokoboon asks, I'm guessing you're going to introduce an IR when you start supporting ARM. Is there any discussion about IR design started internally? If so, what kind of directions are there?
Yeah, definitely. So we've been thinking a lot about that, about designing an IR. I see kind of like 2 possible futures for YJIT, and we still haven't really made the call as to which one we're going to pick. One would be, instead of translating directly from YARV to machine code, we could introduce an IR where we translate YARV into an IR that's easier for us to work with. And then we do the basic block versioning and going to machine code. Another possibility, I think, would be to introduce an IR on the back end so that we translate YARV into this IR using basic block versioning. And then we have like an ARM backend and an x86 backend. So yeah, Kokoboon, if you want to talk about that, like please reach out.
Okay.
You mentioned in one of your slides a profiler called RBSpy. What other tools does your team use for doing these things that we all can use, like memory usage, anything that you can think of off the top of your head?
Right, so I mean, there's RBSpy, there's also StackProf. If you're on Linux, you can use the perf tool.
Okay.
Yeah, and there's also, I didn't really mention this in the slides, but we also added --YJIT-stats. That's what we use internally while working on YJIT to gather some statistics about when YJIT is falling back to the interpreter, for example. So looking at that, you can get kind of a picture of what you can change in your code to make it perform better.
Excellent. Thank you.
Okay. I have another question here from Kokoboon, which is interesting. Maxime, do you and Noah use different benchmark environments? Kokoboon notices that MJIT is still faster than YJIT on opt-caret, and he looks into fixing it. But it's not faster on the YJIT website.
Right, actually, so we have kind of like 2 benchmarking setups. We have one that's called YJIT Bench that's kind of used by developers working on YJIT so that we can make small changes to the YJIT code base, and then we run YJIT Bench, and in something like 20 minutes, it gives us like some performance results. But we also have a website, speed.yjit.org, that uses a different benchmarking harness and does much more lengthy benchmarking. But it also runs on different machines, et cetera, et cetera.
That's time. So thank you, Maxime.
Thanks, everyone.
Thank you, everybody.